A hearty welcome to one and all. We all are moving through the ever increasing global catastrophe, the coronavirus. But in a scientific way of thinking, every event has both positive as well as negative aspects. So, taking this time of gloominess through a positive attitude, our Sacred Heart College Tevara, especially the physics department of our college, has come up with a great initiative to make this corona period a fruitful one and to enhance our scientific knowledge. First of all, I would like to thank Dr. Pius Augustine Sir, who gave us this fruitful opportunity to explore more on our academics and to enhance our knowledge. Today, we are presenting on the topic entropy, which is a famous thermodynamic variable, as we all know, and also which is very interesting, astonishing, and inspiring all at a time. Myself, SIDHIVINAYAK, and in our group, we have Miss KAVYASREE, Miss SWETHA, Miss APARNA PINTO, and Mr. SIBI VARGHESE. The content of our project or the presentation include a small introduction on what is entropy and its general properties, then the change in entropy during various thermodynamic processes, and also the physical concept of entropy, the principle of increase of entropy, and the very famous temperature entropy diagram, the TS diagram, and the way through which we can calculate the efficiency of a Carnot engine, and at last various relationship regarding entropy and the available energy of a system, and the entropy and the disorder of a system. Now, before moving deep into our topic, as an introduction, we have to answer two questions regarding entropy. The first question is, why entropy? It was actually in 1854 that one of the greatest scientists, Rudolf Clausius, who found that the existing variables or thermodynamic variables like pressure, volume, temperature, etc., were insufficient in describing the state of a system. So he also observed that the irreversible nature of one-way processes like the bursting of a balloon or the bursting of a tire, etc. So here, in all these irreversible processes, the reverse process is not possible. So but the existing thermodynamic variables like pressure, volume, temperature can't describe the irreversibility of one-way processes. So he was forced to introduce a new concept, which was later known as entropy in the thermodynamics. Now, the second question is, what is entropy? In higher secondary classes, we might have what defined entropy as the disorganization or randomness of a system and the mixed upness or spread of energy, like that. But it was actually Clausius who gave a specific definition for the concept of entropy. That is, the entropy is the thermal property of a system like temperature or internal energy, or the thermal property of a substance that remains a constant during an adiabatic process. So we can say that adiabatic processes are isoentropic processes. That is, there is no change of entropy during these processes. The unit of entropy was given by him as joule per Kelvin. This is the SI unit, and there are other units like calories per degree Celsius, etc. Now let us see some general properties of entropy. The main and the fundamental property of entropy is that it doesn't obey any conservation laws like energy. Also, entropy of a irreversible process always increases if the system is a closed system. Thus, the universe is traveling towards more unstable state. Hence, it can be called as the arrow of time, like time doesn't move backwards. Likewise, entropy also, or entropy is moving forwards always. That it doesn't, or once the entropy of a system is increased, it can be decreased by any other means. Now, it is a thermal variable like temperature that have been earlier stated, and it's a state function which can only be determined by experiment. Entropy is an experimental concept, but not a theoretical concept like what pressure or anything like that. We can't calculate entropy from applying some equations or anything like that. It can be only studied by experimental setup. Now it's an intensive quantity like the volume, which depend on the size of the system. So entropy depends on the size and structure or the internal composition of a system. So that's all with the basic concept of entropy. Next I pass to SIBI and he will be dealing with the change in entropy and the physical significance of entropy.
Thank you, Siddhi. A warm greetings to all. Now we are going to discuss about the topic change in entropy. Entropy is a measure of degree of randomness or disorder. Entropy is a state function, so change in entropy depends only on the initial and final state. That is, for an example, consider a system having initial state A and final state B. Then change in entropy of that system is given by subtracting the entropy at A from entropy at B. That is given in the equation, that is ds equal to Sf minus Si, where Sf is the entropy of the final state and Si is the entropy of the initial state. Now let's move on to the reversible Carnot cycle. The figure shows the PV diagram of two reversible Carnot cycles. Here L and M are adiabatic curves, T1, T2, T3 isothermal curves, ABCD and DCEF are Carnot's reversible cycle. Q1 heat absorbed at constant temperature T1 and Q2 is equal to heat absorbed or rejected at constant temperature T2. Q3 the heat rejected at constant temperature T3. Here in this graph we can see that T1 should be greater than T2 and T2 should be greater than T3, because in Carnot cycle ABCD, T1 would act as a source temperature and T2 would act as a sink temperature. And in Carnot cycle DCEF, T2 should act as a source temperature and T3 should act as a sink temperature. In cycle ABCD, efficiency is given by eta equal to Q1 minus Q2 by Q1, which is equal to T1 minus T2 by T1. From this we conclude that Q1 by T1 equal to Q2 by T2. Similarly, in Carnot cycle DCEF, efficiency is given by eta equal to Q2 minus Q3 by Q2, which is equal to T2 minus T3 by T2. From this, we again arrive at a conclusion that Q2 by T2 equal to Q3 by T3. By combining these two equations, we can arrive at the conclusion that Q by T would remain as a constant during Carnot cycle. If dQ is a small quantity of heat absorbed at a constant temperature T, then change in entropy ds is given by dQ by T. For a finite reversible change in state from A to B, the change in entropy is given as SB minus SA, which is equal to integral from A to B dQ by T. Entropy of a system is a function of thermodynamic coordinates defining the state of the system. Entropy is also an extensive property because it depends only on the mass of the working substance. For a reversible process at equilibrium, change in entropy ds is equal to Q reversible by T, where Q reversible is the heat absorbed or liberated reversibly. Now let us move on to the physical concept of entropy. Now look at this figure. In this figure we can see that entropy increases as we move upwards. That is, solid state should have the lowest entropy and gaseous state should have the highest entropy. As we move from solid to liquid, we absorb heat and the process is called melting. As we move from liquid to gas, the process is called vaporization, and as we move from solid to gas, the process is called sublimation. All these processes requires an addition of heat. That is, as a system absorbs heat, its entropy also increases. Greater the disorder, higher the entropy. For a given substance, solid state has the lowest entropy because it has the lowest disorder. The liquid state has the intermediate entropy and gaseous state has the highest entropy. Change in entropy is equal to heat added or subtracted by absolute temperature. This is one of the key equations of this chapter. Heat has the same dimension as the product of entropy and absolute temperature. Entropy is also called thermal inertia because it shows the motion of heat. So we can say that the physical concept of entropy is nothing but as heat is added to a system, as more heat is absorbed by a system, its entropy also increases. That is, entropy is proportional to heat added. Now, I welcome SIDHIVINAYAKA to continue with the.
Thank you so much, SIBI. Now let us see the change in entropy during various thermodynamic processes. First, we will consider the case of an adiabatic process. We all know that during an adiabatic process, the system neither rejects nor accepts any amount of heat from the surroundings. So, the heat absorbed or heat rejected dq equal to 0. Thus, from the very definition, ds will be clearly 0. That is, the change in entropy during an adiabatic process is always 0. Thus, the adiabatic processes are known as isoentropic processes. Now, as an alternative process, we will choose the reversible cycles. We all are familiar with the famous Carnot's engine and and the cycle or the Carnot cycle related to it. So, in Carnot's engine or the processes included in the Carnot's engine are isothermal expansion and isothermal compression, adiabatic expansion and adiabatic compression. So in each case, we have to calculate the change in entropy so that after that we can add up these changes to get the total change in entropy during the whole process. So consider that a system is taken from a state A to state B by absorbing an amount of heat dq. Here, the change in entropy is always positive since the process involved is expansion. So, here integral a to b ds equal to plus dq by dt by the definition of the change in entropy. Now, consider the curve BD where the system is taken from the state B to state D by without absorbing or without rejecting any amount of heat as it is a adiabatic process. So here the change in entropy is given by integral B to D ds equal to 0. We have already seen that during an adiabatic process the change in entropy is 0. Now let us consider the curve C to DC where the system is compressed isothermally. That is, the system rejects an amount of heat into the surroundings and then the system is taken from a state D to state C, so that the change of entropy for this process is given by integral D to C ds equal to minus dq by dt. Here there is a negative sign in the right hand side of the equation since the process involved is compression. And at last, consider the curve CA where the system is taken from a state C to the initial stage or initial state A. Here we are actually compressing the system adiabatically. That is, the system neither rejects nor accepts any amount of heat from the surroundings. So here the change in entropy is given by integral C to A ds equal to 0. Now considering the whole process or whole cycle ABCDA, the change in entropy integral ds will be the sum of the equations 1, 2, 3 and 4. That is, the integral ds equal to integral a to b ds plus integral b to d ds plus integral d to c ds plus integral c to a ds. Here the second equation and the fourth equations, as the processes involved are adiabatic processes, change in entropy is clearly 0. So in the final expression we will have only the change in entropies during the isothermal processes, that is integral ds equal to q1 by t1 minus q2 by t2. This is clearly equal to 0 since we have for a reversible engine q1 by q by t is a constant. Therefore, the total change in entropy during a closed reversible cycle is always 0. Now let us see the principle of increase of entropy, and this topic will be dealt by SWETHA. I invite SWETHA.
Thank you, SIDHIVINAYAK. Now let's move on to the topic principle of increase of entropy. Here we consider two engines, irreversible engine and reversible engine. Let Q1 be the heat absorbed at temperature T1 and Q2 be the heat rejected at temperature T2, where T1 is the temperature of the source and T2 is the temperature of the sink. In the case of irreversible engine, the efficiency eta dash can be expressed as eta dash is equal to Q1 minus Q2 by Q1, that is equal to 1 minus Q2 by Q1. And for reversible engine, the efficiency eta can be expressed as eta is equal to 1 minus T2 by T1. By Carnot's theorem, the efficiency of irreversible engine is less than that of a reversible engine working between the same two temperatures T1 and T2. That is, eta dash is less than eta, or 1 minus Q2 by Q1 is less than 1 minus T2 by T1. Cancelling 1 on either side and rearranging the equation, we get Q2 by T2 minus Q1 by T1 is greater than 0. From this, we can infer that source, which is at temperature T1, loses an entropy by an amount Q1 by T1, and sink, which is at temperature T2, gains an entropy by an amount Q2 by T2. Since Q2 by T2 minus Q1 by T1 is greater than 0, we say that there is a net increase in the entropy. Entropy of a system increases in all irreversible processes, and this is known as principle of increase of entropy. All natural processes taking place in the universe are irreversible processes because reversible process is an ideal concept and cannot be achieved. That means the entropy of a universe increases. Therefore, ds of universe is greater than or equal to 0. Now, let us look at a set of few examples which will help us to determine the direction of a process using the thermodynamical coordinate entropy. Here are a set of 3 examples. In the first example, there are 2 blocks A and B. A is at temperature T1 and B is at temperature T2, with T1 greater than T2. The blocks are kept in contact, but the system as whole is insulated from the surroundings. Conduction of heat takes place between the blocks. The temperature of A falls and temperature of B rises, and the thermodynamical equilibrium will be reached. In the second example, there is a flywheel rotating with an angular velocity omega. Its initial kinetic energy is half I omega square. After some time, the wheel comes to rest and the kinetic energy is utilized in overcoming the friction at the bearings. The temperature of the wheel and the bearings rises, and the increase in their internal energy is equal to the original kinetic energy of the flywheel. In the third example, there are 2 flasks A and B connected by a glass tube provided with a stopcock. Let A contain air at high pressure and B is evacuated. The system is isolated from the surroundings. If the stopcock is opened, air rushes from A to B, and the pressure in A decreases and volume of air increases. All the above 3 examples, though different, are thermodynamical processes involving change in thermodynamical coordinates. Also, in accordance with the first law of thermodynamics, the principle of conservation of energy is not violated because the total energy of the system is conserved. It is also clear that with the initial conditions described above, the 3 processes will take place. Let us consider the possibility of the above 3 processes taking place in the reverse direction. In the first case, if the reverse process is possible, the block B should transfer heat to A and the initial condition should be restored. In the second case, if reverse process is possible, the heat energy must change to kinetic energy and the flywheel should start rotating with initial angular velocity omega. In the third case, if reverse process is possible, the air in B must flow back to A and the initial condition should be obtained. But it is a matter of common experience that none of the above conditions for the reverse processes are reached. It means the direction of a process cannot be determined by knowing the thermodynamical coordinates in the 2 ends. To determine the direction of the process, a new thermodynamical coordinate has been devised by the Clausius, and this is known as entropy of the system. So how to determine the direction of a process using entropy? We saw in the previous slide that entropy of a system always increases. That is, ds is equal to q by t2 minus q by t1 is greater than 0. Therefore, the direction of process is taken along where the entropy is positive. And this is how you determine the direction. And that's all with the topic. Next, I pass on to Kavyasree.
Thank you, Shweta. I extend my warm greetings to the listeners. Moving on, our next topic is TS diagram. Interestingly, we are actually well versed with this portion, but presently we are not aware of that. The PV graph on the left hand side, we have seen it many times, is a Carnot reversible cycle showing isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Along with this, we also know that during an adiabatic process, the system won't suffer any entropy changes. So, on moving from 2 to 3 and 4 to 1, our entropy will be same. And also we know that during an isothermal process, the temperature will be remaining constant. That is, from 1 to 2 and 3 to 4, system's temperature will be constant. Next, we are going to plot these points, that is, these ideas. That is what we call as a TS diagram, and it is represented by diagram B. Here, 1 to 2 and 3 to 4 are under constant temperature. Therefore, we have used two straight lines. Similarly, 2 to 3 and 4 to 1 are under constant entropies. Therefore, it's also represented by two straight lines. Next, now, let us divide this TS graph into parts like 1 to 2 as a part, 2 to 3 as another one. Similarly, the other two also. Then we will have 4 parts. Now, let us analyze each one. For the first one, we know that on moving from 1 to 2, our working substance will absorb heat from the source, which is at constant higher temperature. Here, let us call that amount of heat absorbed by the working substance as Q1 and that higher temperature of the source as T1. And let us call that gain in the entropy as S1. Next, from 2 to 3, our entropy change will be 0 as it is an adiabatic expansion. In the third part, let us assume that our working substance rejects Q2 amount of heat at constant lower temperature T2, which will be lower than T1 when compared with it. And from 4 to 1, there won't be any change in the entropy. We have represented that using these 4 equations. On rearranging these equations from the first one, we will get Q1 is equal to T1 into S2 minus S1. Q2 is equal to T2 into S2 minus S1. And then on subtracting second equation from the first one, we can write Q1 minus Q2 is equal to T1 minus T2 into S2 minus S1. Here, the quantity Q1 minus Q2 represents the external work done in the cycle, and T1 minus T2 into S2 minus S1 is the area of the rectangle on the TS diagram. Thus, we can conclude that the area of the rectangle on the TS diagram represents the external work done in the reversible Carnot engine. And now I hope that this portion is clear. Thank you. Next, I pass on the presentation to Aparna Pinto.
Thank you, Kavya. Now, we are going to see how to find efficiency of Carnot's engine using TS diagram. Efficiency of the engine equals work output by heat input. That is, eta equals Q1 minus Q2 by Q1. On the previous slide, we saw that Q1 minus Q2 equals T1 minus T2 into S2 minus S1 and Q1 equals T1 into S2 minus S1. Substituting this on the equation, S2 minus S1 on numerator and denominator is get cancelled and we get eta equals T1 minus T2 by T1 and we can write eta equals 1 minus T2 by T1. Next is physical significance of entropy. First one is entropy is a measure of the available or unavailable energy in the universe. And the second one is it is a measure of the degree of disorder in a system. entropy and available energy. In this, we are going to see how entropy becomes a measure of the available or unavailable energy. We know every natural process is irreversible. Therefore, entropy tends to increase. The second law of thermodynamics is also called as the principle of degradation of energy. Why is it called so? The second law tells us that the total amount of energy of any substance is not convertible into useful work. There is always an energy loss. A portion of the whole energy which is used for doing useful work is called available energy. The remaining part of the energy which cannot be converted into useful work is called unavailable energy or energy loss. This unavailable part of energy can be in the form of heat through friction, conduction, radiation, etc. When we consider a heat engine, no heat engine can have 100% efficiency, even under ideal conditions. In a heat engine, if energy is transferred to the system, then all energy cannot be converted to the work. Some will move in the sink. Hence, there must be loss of energy to the sink without which the system can't work. Thus, the energy is said to be degraded. And so the second law of thermodynamics is also called as the principle of degradation of energy. Simply saying, principle of degradation of energy implies that although the total energy of the universe is conserved, it is transformed into unavailable energy. As entropy increases, unavailable energy also increases, but available energy of the universe will tend to zero. We can say entropy is a measure of unavailable energy. If entropy keeps on increasing, it will eventually reaches a maximum value. It will lead to the heat death of the universe. Heat death, which is also called as big chill or big freeze, occurs as the universe moves towards maximum entropy. It is considered as one of the theories which explain how the universe will end. Next is entropy and disorder. Entropy is said to be a measure of disorder or randomness of a system. With increase in entropy, disorder of the molecules of the substance increases. That is, we can say increase in entropy is the transition from ordered state to disordered state. For example, in this figure, molecules are arranged more orderly in solid. So there is low disorder, hence low entropy. In gas, molecules are arranged randomly, so high disorder, hence high entropy. When a solid changes to liquid, an increase in entropy takes place because orderly arrangement of molecules breaks in crystal to the less orderly liquid state. Hence, randomness increases. When vaporization takes place, there is a further increase in randomness in the distribution of molecules. Hence, entropy increases. So, we can conclude that more disorder equals more entropy and more order equals less entropy. The entropy is a measure of the degree of disorder in a substance, just as the temperature is a measure of the degree of hotness of a body. From this TS diagram, it is evident that as temperature of the system increases, entropy increases, hence disorder increases. Temperature and entropy are connected. That is the reason why it is said that the entropy is a measure of the degree of disorder in a substance, just as the temperature is a measure of the degree of hotness of a body. We know that when temperature decreases, entropy decreases. At 0 Kelvin, disorder decreases, hence entropy tends to 0. So, at absolute 0, entropy of a substance is 0. So, that's all about the physical significance of entropy. I hope you all understood. Now, we have come to the end of our presentation. Let's recap on our topic. Entropy is a thermal property of a substance that remains a constant during an adiabatic process. Entropy is an experimental concept and not theoretical. Change in entropy is difference between final entropy and initial entropy. When heat increases, entropy and disorderness increases. Entropy of a system always increases, and this is known as the principle of increase of entropy. Entropy helps to determine the direction of a thermodynamical process and is taken along where entropy is positive. TS diagram is a representation of Carnot cycle. Last is, entropy is a measure of available or unavailable energy in the universe and degree of disorder in a physical system. I hope it's clear. We will wind up our presentation with a quote by Martin Luther King Jr. He says, "The ultimate measure of a man is not where he stands in the moments of comfort and convenience, but where he stands at the times of challenge and controversy." Now, I thank everyone for cooperating and patiently listening to us. Thanks to Professor Pius Augustine for giving us this valuable opportunity. Thank you all.